Good morning. Today, I'd like to play another game, very much in the spirit of what we were doing in the previous video. We're going to have pairs of numbers again. We'll regard these as being fundamental objects, and I want to investigate what we can figure out about these things without letting the other shoe drop yet. I'm going to let capital K be the collection of all pairs of numbers A and B, where A and B are real numbers. In this setting, I don't care if any of them are 0 or not, except in one special situation that we'll talk about later. To keep from getting confused about this new set of things versus the first one, instead of using parentheses, I'll use square brackets instead. Those of you who know linear algebra could think of these things as being row vectors in R2. I want to define arithmetic on these objects: addition, subtraction, multiplication, and multiplication by a real number. I'm going to define these things in the following way. If I take two elements out of this set K, A comma B and C comma D, I'll define addition this way. AB plus CD is A plus C, B plus D. Likewise, AB minus CD is A minus C in the first slot, and B minus D in the second. Thirdly, a real number alpha multiplied by one of these AB quantities is the quantity alpha A comma alpha B. If this were all there were to it, this would basically be vector calculations in two-dimensional space, just like you did back in Calc 3. We're going to have a notion of multiplication that is different than what we had back in Calc 3, though. Given any four real numbers, A, B, C, and D, I can form the quantity bracket AB bracket and the quantity bracket C comma D bracket. This is going to be one of the objects out of K. The number in the first position is going to be AC minus BD, and the number in the second position is going to be AD plus BC. At this point, it's worth mentioning that it looks very much like I'm just making stuff up out of thin air. We have to keep focused on the logic of this. K is a set of things. I'm just defining addition, subtraction, and really two different types of multiplication here. This is perfectly logically consistent with what we've done earlier. The issue is whether or not it's useful for anything. That isn't clear at the onset, and it isn't clear what advantages that this will bring. We'll wait and see about that. In the meantime, in ordinary algebra, there are certain things that you expect to be true. Addition is supposed to be commutative, so is multiplication. Multiplication is also supposed to be associative, and you should have a distributive law. Let's check a few of these things. One thing that we can check is, in K, does addition obey a commutative law? That is to say, is it true that AB plus CD is always the same as CD plus AB? At first glance, this seems like a silly thing to check, but these are new objects that we're messing with, and it's not completely clear that this should be true. I can use the definition of addition to actually write out the two sums that I'm interested in. Bracket AB plus bracket CD is bracket A plus C, comma B plus D, while bracket CD plus bracket AB is bracket C plus A, D plus B. A, B, C, and D are just ordinary real numbers, though. So A plus C and C plus A are the same thing. And B plus D and D plus B are the same thing as well. So the corresponding entries in this object and that object are the same. That means that the two things are equal to each other, regardless of what A, B, C, and D are. In K, there is a commutative law for addition. In third semester calculus, you learn about the cross product of vectors. You're introduced to the notion of the cross product, and then almost immediately you find out that there's some rather bad news. U cross V is not generally the same as V cross U. In fact, they're negatives of each other. There is no commutative law of multiplication for the cross product. But even worse, U cross the vector V cross W is generally not equal to the vector U cross V cross product with W. The reason that it's worse is, at least in the first fact, there's some simple relationship between U cross V and V cross U, but in that second fact, there isn't. As a result, I am not 100% confident that there's going to be some sort of associative law for multiplication in this new set K. Maybe there is, maybe there isn't. I want to either convince myself that this equation is always true, regardless of the values of A, B, C, D, E, and F, or I want to be able to observe that it's not necessarily true. In view of what happened with the vector cross product, I don't know which way this is going to go ahead of time. Firstly, I'll calculate the left-hand side of this equation. The product CDEF is direct to write down because of our multiplication rule. The product of AB with that quantity, though, is kind of a mess. If you look at the pattern in the definition, I'm supposed to take the first number and the first number and multiply them together. Then I'm supposed to subtract away the second number times the second number, so we'll write that down. In the second position of this awful looking product, I'm supposed to have this number times that number plus that number times this number. So if you write all of this stuff out, you get the middle line. Then, since A, B, C, D, E, and F are just ordinary numbers, I can use ordinary algebra to write out whatever is in the first position of the left-hand side of this equation, and also figure out what's in the right-hand position. This is what the left-hand side of this equation looks like, written in as simple a term as I can make it look. For the right-hand side of the equation, first we'll figure out what A, B, C, D is, and once we have that, we'll multiply it by bracket EF to get the right-hand side of the equation. Doing the same multiplication that we did before, we get this expression for this quantity. We can compare one term at a time in both of these positions the numbers that we get. In the first case, we had a term ACE, and we have one there. Here we have minus b times d times e, and there we have the same term. Here we have minus ADF, and minus BCF, minus BCF. The two objects out of K have the same number in the first position. Meanwhile, in the second position, ACF and ACF minus B times D times F minus B times D times F plus A times D times E plus B times C times E. The left-hand side of that equation is always equal to the right-hand side, so multiplication is associative. There are a number of other properties that you can investigate, but I'm going to leave those as an assignment. The usefulness of the idea in the first game that we played was we were able to do things in our new number system that you were not able to do in the first one. So, for instance, in the integers, the idea of 7 divided by 3 doesn't make a whole lot of sense, but once we moved up into the pairs of numbers with the parentheses around them, with the arithmetic defined in the way that we did, suddenly we can make sense out of 7 over 3 and 3 over 7 and all other rational numbers. The thing that made that useful, in addition to the rules of addition, subtraction, multiplication, were that there was a subset of set F that we were talking about previously that you could identify with the integers. Now, the numbers that are in our brackets, the pairs of numbers, these are real numbers. There's going to be some things that you can do in this new system that you couldn't do in the reals, but it's important to figure out that there's a subset of the things out of K that act just like the real numbers. In a sense, then, K is to the reals as F was to the integers. Our subset will be called L for now. It's going to be the collection of all bracket AB quantities, where A is a real number. B is also a real number, but not just any real number. B has to be 0. I want to think about what would happen if you took things like this and applied the rules of addition, subtraction, multiplication to them. The results are informative. Bracket A0 plus bracket C0 is bracket A plus C0. If you do the subtraction, something similar happens. Alpha times A is alpha A, alpha times 0 is 0, and if you carry out the multiplication, A0, C0, when the dust settles, you just get A times C, 0. All of these quantities have a 0 in the second position, and since we now know what it is, we can ignore it and think A plus C, A plus C, A minus C, A minus C, alpha times A, alpha times A, and A0, C0 is AC, comma 0. When I add two things out of L, I just add the real numbers in the first position. Here, I subtract. Here, I multiply the first position by alpha. Here, I multiply the first positions together. This is exactly how real number arithmetic works. So just like back in set F, we're going to have a mental equivalence here. Anytime I have something out of L, since I know the second number is 0, I'm going to associate that with the actual honest-to-goodness real number, A. Bracket A0, I'll just think of it as the number A. This is very similar to what happened when we eventually started thinking of open parentheses A comma B as being, in our much more familiar notation, a horizontal bar B. There's only one issue here. What about all the other things where the second thing is not 0? In view of the way we add these bracket quantities together, I can write bracket AB as bracket A comma 0 plus bracket 0 comma B, and we've made an agreement with ourselves that when we see these sort of things, we'll just think of them as being real numbers. These things, it has a non-zero thing in the second position rather than the first, so this bracket 0, 1 is not one of these real numbers, not even in our association way of thinking about it. I'll just mention in a sidebar, does bracket 0, 1 have any interesting properties? I'm not going to answer that because I'm going to make it part of the first homework assignment. We'll come back to that, though. That's what makes all of this more interesting than it seems at first. There's something that you can do with these K objects that you couldn't do in various other settings. In the real numbers, as long as C isn't 0, A equal B over C means the same thing as B equals C times A. I'd like to figure out if there's some sort of corresponding thing going on with these K bracket objects. Given two of these objects out of K, AB and CD, can I always, or almost always, find a K object, EF, so that AB is EF times CD? If so, I'll make up a new name for that, just as we did with the rational numbers. If I can do this, I'll call the result bracket AB divided by bracket CD. And I want to mention again, I have no idea at this moment whether or not it's possible to do this. If it is possible to do it, I don't know if there's only one way to do it for a given pair AB and CD. If I write out the multiplication that I want to be true, for this to work, that number and that number must be the same. Also, that number and that number must be the same. Keep in mind that allegedly we already know A, B, C, and D, and we're trying to rig up E and F so that this will happen. I can write that as a linear system of equations, and then more revealingly, I can write it in matrix form. I'm going to have a unique solution, EF, for given A, B, C, D, exactly when this system of equations has a unique solution. That's going to happen when its determinant is not 0. If you calculate that determinant, though, it's just C times C minus D times the negative of D. That's C squared plus D squared. Since C and D are real numbers, the only way that that could come up equal to 0 is if both C and D were 0. So can I find such an EF and have it be unique? as long as the CD isn't the additive 0 in set K, then the answer is yes. Moreover, I can actually get the solution by doing Cramer's rule. So carrying out my Cramer's rule plan, E must be AC plus BD over C squared plus D squared, and F must be EB minus DA over same C squared plus D squared. Using the number times bracket quantity idea, I can pull the 1 over C squared plus D squared out front, but then looking at what's left, that looks awful familiar. Let me remind you of something. If I look at A, B, C, D, the numbers in the two positions are AC minus BD and AD plus BC. These are almost those numbers, except every term that has a D in it has had its sign reversed. Let's think about that. What if I multiply AB by not CD, but C comma negative D? I've flipped the sign on the number in the second slot. After working through the arithmetic, I get AC plus BD, AC plus BD, BC minus DA, BC minus D times A. This bracket quantity is a product of two things out of K, one of which is the top of the fraction that we're trying to figure, and the other one but has been altered a little bit. So I'm going to make up a new word. The conjugate of CD is C comma negative D, and I'm going to make up a symbol for it. I'll write CD with a horizontal bar above it, pronounced conjugate of bracket CD. We're very close to dropping all pretense here. There's one more interesting feature about this. The bottom of that fraction is a real number. It's C squared plus D squared, but it's related to this conjugate thing as well. If I take one of these K objects, CD, and multiply it by its conjugate, C negative D, after I work through all of the arithmetic, the number in the second position comes up 0, which means we can interpret this thing as an actual number, the value of which is C squared plus D squared. This is what's on the bottom of that fraction we were just looking at. Writing all of our results, we get this. It's tempting to think that you could make life easier on yourself by canceling out the conjugate of C comma D. While logically valid, you wouldn't want to do that because that's just going to give you an equation that says AB divided by CD is AB divided by CD, and that won't be of any use to you. But if you leave it as is, I can reduce this down into one of the objects out of the K set. We now know how to do addition, subtraction, multiplication by a number, multiplication of two of these things, and division. Moreover, we have an identification that all of the things that have a number in the first slot and a 0 in the second is associated with a real number. I'm going to put the interesting bits in the homework assignment, so I'm going to stop here. I hope everybody's having a good day, and I'll talk to you again soon.